Welcome to the Mastering Object-Oriented Programming course. This 4-week journey will equip you with the skills to build scalable, reusable, and maintainable software solutions. Let's get started. Object-oriented programming is the backbone of modern software development. It empowers developers to write scalable, reusable, and maintainable code. Mastering OOP is essential for understanding frameworks, APIs, and large-scale systems. Over 4 weeks, this course will take you from OOP fundamentals to advanced design principles and real-world applications. Each week focuses on a specific theme to ensure a comprehensive learning experience. By the end of this course, you will understand key OOP concepts such as encapsulation, inheritance, and polymorphism. You will also explore advanced techniques like design patterns and solid principles, all while gaining hands-on experience through projects. Our approach includes conceptual lessons, interactive exercises, quizzes, and practice days. You will also work on mini projects to solidify your understanding and build real-world applications. This course is designed for beginners starting with OOP, intermediate developers looking to refine their skills, and professionals preparing for interviews or advancing their careers. All you need is a basic understanding of programming, a computer with your preferred development environment, and the determination to learn and grow. Embark on this exciting journey to master OOP. By the end of this course, you will have the skills to create scalable, maintainable, and efficient software solutions. Let's dive in and start learning today. Welcome to the introduction of Object-Oriented Programming or OOP. In this course, we will explore the fundamentals and advanced concepts of OOP, providing you with the tools to write cleaner, more efficient, and modular code. Object-oriented programming is a programming paradigm based on the concept of objects. These objects can contain both data, known as attributes, and methods, which represent the behaviors of the objects. OOP helps us organize complex software systems into smaller, manageable units. With OOP, you can create reusable and maintainable code by modeling real-world entities. So, why should we use OOP? First, it allows us to model real-world entities like cars, animals, and buildings in a way that is easy to understand. OOP also promotes code reuse, modularity, and scalability. When your code is structured properly, it becomes easier to maintain and extend over time, making it a great choice for large and complex systems. Let's now look at the 4 key principles of OOP: encapsulation, abstraction, inheritance, and polymorphism. Encapsulation involves hiding the internal state of an object and only exposing it through methods. This ensures data is accessed and modified in a controlled manner. Abstraction simplifies complex systems by hiding unnecessary details and exposing only essential features. Inheritance allows us to create new classes that reuse the properties and methods of existing ones, promoting code reuse. And polymorphism enables objects to take on different forms, making your code more flexible and dynamic. Now let's compare OOP with procedural programming. In procedural programming, we organize code around functions or procedures. In OOP, we organize our code around objects which combine both data and behaviors. OOP is especially useful when building large systems as it promotes modularity and reusability, while procedural programming can become harder to manage as the system grows. To understand OOP better, let's look at some real-world examples. Imagine a car object. It has attributes like brand, color, and engine type, and behaviors like start, stop, and accelerate. Similarly, if smartphone can have attributes like screen size, battery level, and brand, with behaviors like making calls, sending messages, and browsing the web. These objects are the foundation of OOP. To recap, OOP revolves around four core concepts: encapsulation, abstraction, inheritance, and polymorphism. Encapsulation protects data, abstraction simplifies complex systems, inheritance promotes code reuse, and polymorphism allows objects to take multiple forms. These principles form the basis of OOP and will be explored in more details as we move through the course. Now it's your turn. Pick a real world object and identify its attributes and behaviors. For example, consider a laptop. It might have attributes like brand and processor type and behaviors like start, shut down, and run programs. This exercise will help you connect real world entities to object oriented code. To summarize, today we have introduced the concept of OOP. We have learned about its core principles: encapsulation, abstraction, inheritance, and polymorphism. These principles will help us organize and manage complex code more effectively. In the next lesson, we will dive deeper into each concept. Here's an inspiring quote to wrap up today's lesson. The goal of object-oriented programming is to make software more modular, reusable, and maintainable. When you design your code to be more like the real world, it becomes easier to understand and evolve. This quote emphasizes how OOP makes code easier to work with and extend. Welcome to day 2 of our object-oriented programming course. Today, we will dive into the core concepts of classes and objects in OOP. We will explore how these fundamental building blocks of OOP allow us to model real-world entities and define their behaviors. Let's get started. Let's begin by understanding what a class is. A class serves as a blueprint or template for creating objects. It defines the structure and behavior of an object by specifying its attributes and methods. For instance, consider a car class. It may have attributes such as brand and color, and methods like start and stop. A class is where we define the properties and actions that our objects will have. An object is an instance of a class. When we create an object, we are essentially creating a specific entity based on the class blueprint. For example, using the car class, We can create objects like car 1 a red Toyota and car 2 a blue Honda. Each object holds specific data but follows the same structure defined by the class. Now let's look at the syntax for creating a class. Here's an example of how to define a class in C++. We start by using the keyword class followed by the class name like car. Inside the class, we define public attributes and methods. In this example, the car class has two attributes, brand and color, and two methods, start and stop. These methods define the actions that objects of this class can perform. Once we have our class, creating objects is simple. You just declare an object by using the class name followed by the object name. For example, car, my car creates an object of the car class. After that, you can access the attributes and methods of the object like myCar.start to make the car start. Here's an exercise for you. Try creating a car class, define attributes such as brand and color, and add methods like start and stop. The goal here is to practice using classes and objects. Make sure the methods display a message when called. Let's go over an example solution. In this code, we create the car class with attributes brand and color and methods start and stop. The start method will print a message indicating that the car is starting, while the stop method will display a message that the car is stopping. You can see how we create the myCar object and use its attributes. To summarize, a car is a blueprint that defines the structure and behavior of objects, while an object is a specific instance of a class. The class allows us to define attributes and methods, and objects are created from that class to hold real data and interact with the methods. These are the core concepts that you will use in object-oriented programming. Today, we learned about classes and objects. We saw that a class defines the structure of an object, and an object is a real-world instance that follows this blueprint. We also practiced creating classes and objects in C++ and learned the basic of syntax. Tomorrow we will dive into encapsulation, one of the key principles of OOP. For today's exercise, think of another real-world object and define its attributes and methods. For example, you could create a laptop class with attributes like brand, processor, and RAM, and methods like turn on and shut down. This will help reinforce the concepts of classes and objects. As we wrap up today's lesson, here's an inspiring quote to keep you motivated. The best way to predict the future is to create it. Keep building and keep learning and stay passionate about your journey in programming. Thank you for your time. Welcome to day 3, Understanding Encapsulation in Object-Oriented Programming. In this session, we will explore the key concept of encapsulation, how it benefits our code, and walk through some practical examples. Encapsulation is a fundamental concept in object-oriented programming where we bundle data and the methods that operate on that data into a single unit, which is the class. It helps us hide the internal state of an object and only expose what is necessary to the outside world, ensuring better control and security of data. Access modifiers control the visibility of data within a class. There are three main types: public, private, and protected. Public allows access from anywhere in the program. Private restricts access only to the class itself, and protected allows access within the class and its derived classes. Encapsulation offers several benefits, including data hiding, control over data modification, and flexibility. By preventing unauthorized access and reinforcing validation, we can improve the security and maintainability of our code. To control access to private data, we use getters and setters. Getters allow us to retrieve the value of a private attribute, while setters allows us to modify the value, often with additional checks and limitations to ensure data integrity. Let's look at a practical example, the car class. This class uses getters and setters to control access to the private speed attribute. The setter ensures that only positive values are assigned to the speed, preventing invalid input. Here's the code for the car class. We define a private attribute speed and provide a getter method to access it. This ensures that only authorized methods can modify the speed of the car. Now we implement the setter method. This method checks if the new speed is positive before setting it. If it's not, it shows an error message. This illustrates how encapsulation helps control the flow of data and ensures data validation. Encapsulation brings several advantages, including preventing unauthorized access to sensitive data, simplifying code maintenance, and improving the reusability of components. By isolating the internal workings of a class, we ensure that changes to the internal structure do not affect other parts of the system. Now let's put this into practice with an exercise. Create an employee class with private attributes such as name and salary. Use getters and setters to control access to these attributes and add validation to ensure salary is always positive. Here's the first part of the employee class code. We define the private attributes and provide getter and setter methods for the name attribute. These methods allow controlled access to the employee's name. Next, we add the salary related getter and setter methods. The setter ensures that the salary is positive before assigning it, preventing invalid data from being set. To wrap up, here's a motivational quote by Alan Kay. The best way to predict the future is to invent it. Just like encapsulation helps us control the flow of data in our programs, we have the power to design and shape the future of our projects. Thank you for joining this session on encapsulation in OOP. I hope you now have a deeper understanding of this concept and its importance in writing secure and maintainable code. Happy coding! Welcome to day 4 of our object-oriented programming course. Today we will dive into the essential concepts of constructors and destructors. We will understand what they are, how they work, and why they are crucial in object-oriented design. Let's start with constructors and destructors. A constructor is a special function that is automatically invoked when an object is created. It's used to initialize the object's attributes or allocate resources. On the other hand, destructors are functions that are automatically called when an object is destroyed. Their primary role is to release any resources the object has acquired, such as closing files or freeing memory. Let's explore the different types of constructors. First up is the default constructor. This constructor does not take any arguments and initializes an object with default values. For example, if we have a car class, a default constructor might initialize the car's brand to unknown and year to 2020. Next, we have the parameterized constructor. Unlike the default constructor, this one accepts parameters to initialize the object with specific values. For example, you might create a car object with a specific brand and year, like Toyota and 2023. By passing these values as arguments when creating the object. Now let's talk about the copy constructor. This constructor is used to create a new object as a copy of an existing one. It's particularly useful when you need to pass or return objects by value, ensuring that the new object is a duplicate of the original one, without just copying the pointer to the original one. Destructors are the counterpart to constructors. They are called when an object is about to go out of scope or when it's explicitly deleted. Their purpose is to clean up the resources that the object may have acquired during its lifetime. In C++, destructors are defined using the class name preceded by tilde symbol. Constructors are used when an object is created, either as a local variable or when it's dynamically allocated. Destructors are used when an object is destroyed, either when it goes out of scope or when it's explicitly deleted by the programmer. These functions ensure that objects are properly initialized and cleaned up. Now let's put our knowledge into practice. For today's exercise, create a class named book with 3 attributes: title, author, and price. Implement a parameterized constructor to initialize these attributes. And don't forget to include a destructor that displays a message when the book object is destroyed. Let's now look at the benefits of using constructors and destructors. Constructors ensure that objects are initialized with valid values, and destructors help manage resources, preventing memory leaks. Together, they make your code more reliable, clean, and efficient. To summarize, constructors are essential for initializing objects when they are created, and destructors help with the resource cleanup when objects are destroyed. These concepts are foundational to object-oriented programming and are vital for writing well-structured, memory-efficient code. That wraps up today's lecture on constructors and destructors. Be sure to practice creating and using constructors and destructors in your own projects to get a deeper understanding. Keep learning, and I will see you tomorrow for more OOP concept. Welcome to day 5 of our object-oriented programming journey. Today, we will dive into static members, understanding how static variables and methods work in OOP and when to use them. Let's start by defining what static members are. In object-oriented programming, static members are variables or methods that belong to the class itself, rather than to individual instances of the class. This means that you can access them directly from the class without creating an object. First, let's talk about static variables. Unlike regular instant variables, static variables are shared across all instances of a class. They retain their value between method calls and can be accessed without creating an object. For example, consider a class that tracks how many objects have been created. The static variable will keep count of all objects created from that class. Now let's move on to the static methods. Static methods can be called directly on the class without the need for an instance. However, they can only access other static members of the class. Static methods are often used for utility functions that do not depend on object-specific data. So, when should you use static members? Static members are useful when you need to track data shared across all instances of a class. For instance, if you need to count the number of objects created, or if you have utility functions that don't depend on the object's state. Let's look at a practical example. Imagine you have a counter class. You want to track how many times a method is called. By using a static variable to store the count and a static method to retrieve it, you can easily achieve this. Static members offer several benefits. They optimize memory usage because the variable is shared across all instances. They also allow for utility methods or data that are common to all objects. For example, tracking the total number of created objects. Now it's time for an exercise. Create a counter class with a static variable that tracks how many times a specific method is called. Implement a static method to retrieve the count and test it by printing the result after multiple method calls. In conclusion, static methods are powerful tools in OOP. They belong to the class rather than individual instances and can help manage shared data or functionality. Static variables are shared across instances, while static methods can be used without creating an object. Use static members when you need shared data or behavior across all instances of a class. Before we end today's lesson, here's a motivational quote. Success is a sum of small efforts repeated day in and day out. Keep practicing and you will continue making progress. Welcome to day 6 of our object-oriented programming course. Today is practice day, where we will focus on solving problems that involve object creation, encapsulation, and constructors. Let's get started and dive into the exercises. For our first problem, we will create a bank account class. The goal is to design a class with methods for deposit, withdrawal, and displaying the account balance. This will help us practice working with class methods and encapsulation. In our bank account class, we will define private attributes like account number, account holder name, and balance. We will create public methods for deposit, withdrawal, and displaying the balance. This is an example of encapsulation where we control how data is accessed and modified using getter and setter methods. Here's an example of how we might implement the bank account class in code. We initialize the class with account details and then we can deposit, withdraw, and display the balance. Notice that we use methods to control access to the balance, ensuring it cannot be changed directly outside of these methods. Next, we will work on another problem where we create a class that has private attributes and provides controlled access through methods. This exercise will further solidify our understanding of encapsulation, which is a key principle of object-oriented programming. In encapsulation, we define private variables within the class, making them inaccessible from outside. We provide public getter and setter methods to allow controlled access. This ensures that our class internal state remains safe and secure from accidental changes. Today we have focused on solving problems involving object creation, encapsulation, and constructors. We have learned how to build classes with private attributes and how to control access to these attributes. Understanding encapsulation is crucial for writing secure and maintainable code. To wrap up, we practiced designing classes with encapsulation, allowing for controlled access to class properties. We also worked on common tasks like deposit and withdrawal for a bank account class. These exercises will help you build strong foundational skills in object-oriented design. In our next lessons, we will continue to build on these concepts and tackle more advanced topics. Welcome to day 7, where we focus on consolidating your understanding of the key concepts covered in week 1. Today's session will be divided into 2 parts, a multiple choice quiz to test your knowledge and a comprehensive recap of the topics we have covered so far. Let's begin with the multiple choice quiz. This quiz will cover the essential topics we have learned during week 1. The questions will test your understanding of what object-oriented programming is, its core concepts like encapsulation, abstraction, inheritance, and polymorphism, as well as the differences between classes and objects. Additionally, you will recall concepts such as constructors, static members, and how to implement encapsulation to protect an object's internal state. Get ready to challenge yourself. Now let's take a step back and review week's, week one's core concepts. We started by understanding object-oriented programming or OOP. OOP models real-world systems, allowing for easier structure and maintenance. It focuses on objects which encapsulate both data and behavior. This week we have seen how OOP helps us organize and manage code effectively. Encapsulation and abstraction are key concepts in OOP. Encapsulation allows us to protect an object's integral state, providing controlled access through getters and setters. This ensures data integrity and security. Abstraction, on the other hand, hides the complex implementation details and exposes only the essential features of an object, making it easier for users to interact with it without worrying about the inner workings. Inheritance and polymorphism take OOP to the next level. Inheritance allows a class to inherit properties and behaviors from another, promoting code reusability. We explored single, multi-level, and hierarchical inheritance. Polymorphism enables objects of different classes to be treated as objects of a common subclass. This concept allows for method overriding and function overloading, making code more flexible and dynamic. Next, we looked at constructors and static members. Constructors are special methods used to initialize objects, ensuring they start with valid data. We also learned about static members, which are shared across all instances of a class. Static variables and methods can be accessed without creating an instance of the class, making them useful for tracking global states like the count of created objects. To reinforce what we have learned, we have a recap challenge for you. Your task is to refactor a poorly designed class by applying the principles of encapsulation and utilizing static members where necessary. Additionally, try creating a real-world system like a library or banking system using the concepts we have covered in week 1. This exercise will help solidify your understanding of how to structure OOP applications. That concludes our day 7 session. Remember, the quiz and recap are designed to help you consolidate your understanding of week's 1 OOP concepts. Take the time to reflect on what you have learned, revisit any areas where you feel unsure, and make sure you are comfortable with the core OOP principles like classes, objects, constructors, and static members. With this solid foundation, you are ready to move on to more advanced OOP topics in the coming weeks. Welcome to our session on inheritance in object-oriented programming or OOP. In this lesson, we will explore the concept of inheritance, its benefits, and different types of inheritance in OOP. Inheritance is one of the core concepts in OOP. It allows a class to inherit properties and behaviors from another class. The class that inherits is called the child class, while the class from which it inherits is called the parent class. This mechanism enables code reuse and promotes a hierarchical relationship between classes. The primary benefit of inheritance is code reusability. You can extend the functionality of existing code without modifying the original class. This promotes cleaner, more maintainable code. Additionally, inheritance helps establish a hierarchical structure which mirrors real-world relationships and is a powerful way to model objects. In single inheritance, a class inherits one from one parent class. This is the simplest form of inheritance. For example, a dog class can inherit from an animal class, but a dog will have all the properties and methods of the animal, but it can also add its unique features. In multi-level in multi-level inheritance, a class inherits from a class that already inherits from another class. Think of it like a chain of inheritance. For example, a child class can inherit from a parent class, which in turn inherits from a grandparent class. This creates a hierarchy of classes. In hierarchical inheritance, multiple classes inherit from a single parent class. For example, both a dog class and a cat class might inherit from an animal class. This allows both the dog and cat to share common behaviors from the animal, while each class can still have its specific traits. Multiple inheritance allows a class to inherit from more than one parent class. Although this feature isn't supported in all programming languages, it can be powerful in scenarios where a class needs to combine functionalities from different sources. For example, a hybrid class might inherit from both class A and class B. To implement inheritance in most OOP languages, we use access specifiers like public, protected, and private. Public members of the parent class are accessible in the child class, while protected members are also accessible but can't be used by outside code. Private members are not accessible in the child class. The child class can inherit properties and methods from the parent class, making it easy to reuse code. In inheritance, the derived class does not automatically inherit the constructor of the base class. However, you can call the base class constructor explicitly in the derived class using an initialization list. This ensures that the parent class is properly initialized when the child class is created. Now let's put this into practice. Create a base class animal that has common attributes like name and methods like it. Then derive dog and cat classes from animal, adding specific behaviors like bark for the dog and mew for the cat. This exercise will help you understand how inheritance works in real-world scenarios. To recap, inheritance is a key concept in OOP that allows classes to share common behaviors and properties. There are several types of inheritance: single, multi-level, hierarchical, and multiple inheritance. Inheritance helps reduce code duplication and creates a more organized class hierarchy. We also discussed constructor inheritance and how to use access specifiers to control access to base class members. In our next session, we will dive deeper into method overriding and the super keyword. We will see how derived classes can override methods from the parent class to avoid specific implementations, and how super allows us to call parent class methods from within the child class. Welcome to day 9 of our object-oriented programming course. Today we will be diving into the concept of method overriding and the use of the super keyword. Let's start by understanding what method overriding is. In object-oriented programming, method overriding occurs when a subclass provides its own specific implementation of a method that is already defined in its superclass. Essentially, we are replacing the inherited method with your own customized version. This allows us to modify or extend the behavior of an inherited method without changing the original class. Here are some key points to keep in mind about method overriding. The method signature, name, return type, and parameters must remain the same. Overridden methods should have the same or greater level of accessibility in the subclass. Static methods cannot be overridden. Using the at the rate override annotation helps ensure that the method is correctly overridden, reducing errors. There are several benefits to method overriding. First, it allows for customization. Subclasses can modify inherited behavior to better suit their needs. Second, overriding provides flexibility as subclasses can adopt while still following the parent class interface. Finally, overriding supports dynamic dispatch, meaning the method call is resolved at runtime, making your programs more flexible. Next, let's talk about the super keyword. In object-oriented programming, the super keyword is used to refer to the parent class. It allows subclasses to call methods and constructors from their parent class, even if those methods are overridden in the subclass. For example, if we want to invoke a method from the parent class inside an overridden method, you can use super.methodName to do so. Let's take a look at an example to illustrate overriding and the use of the super keyword. Consider the superclass animal that has a method called sound. The subclass dog overrides this method but also wants to call the parent's sound method before adding its own behavior. In this case, it uses the super keyword. Now let's test these classes in the main program. If we create an instance of dog and call the sound method, it will first call the animal's sound method through super and then add its behavior. Now, now that we have covered the basics, let's put our understanding into practice. Here's an exercise for you. Create a class called vehicle with a method called start engine. Then create two subclasses car and motorcycle and override the start engine method in each class. Don't forget to use super to call the parent class method. Let's take a look at the expected output from our exercise. In the main program, create instances of car and motorcycle. When you call the start engine method, you should see the following output. Vehicle engine started, car engine started, motor engine started. This shows how the subclass can customize the behavior of the parent class while still retaining some of the original functionality. To summarize today's lesson, method overriding allows subclasses to provide their own implementation of a method defined in the superclass. The super keyword is used to access parent class methods or constructors from the subclass. Method overriding provides flexibility, customization, and dynamic dispatch, making it an essential concept in object-oriented programming. This concludes day 9 of our course on object-oriented programming. Make sure to practice overriding methods and using the super keyword in your projects. We will continue building on these concepts in the coming days. See you next time. Welcome to day 10 of our object-oriented programming course. Today we will dive into the concept of abstraction, one of the core principles of O. We will explore what abstraction is, its types, and how it helps simplify complex systems. Let's begin. At its core, abstraction is the process of hiding the complex details of a system and exposing only the essential features. It allows you to build on high-level functionalities without getting bogged down by low-level implementation details. Think of it as using a remote control without needing to understand the circuits inside. A real-world example of abstraction is driving a car. When you drive, you don't need to know how the engine or transmission works. You just interact with the steering wheel, pedals, and controls. This is abstraction in action. You are interacting with a simple interface while the complex details are hidden. In object-oriented programming, there are two main types of abstraction: abstract classes and interfaces. Let's understand both in detail. An abstract class is a class that cannot be instantiated on its own. It can have both abstract methods, which must be implemented by subclasses, and concrete methods, which have a default implementation. This is useful when we want to provide a common base class with some default functionality while still enforcing specific implementations in derived classes. Here's an example of an abstract class in Java. We define an abstract class called shape with an abstract method draw. This method will be implemented by the derived classes such as circle or square, while the base class shape must also have concrete methods like move that can be inherited directly. Let's take a look at how we implement abstract classes. In this example, we have two derived classes, circle and square, both of which override the draw method to provide specific implementations. The shape class defines the structure, but it's the subclasses that provide the detailed behavior. Next, let's talk about interfaces. An interface defines a contract of behavior. Unlike abstract classes, interfaces don't provide any implementation. Any class that implements an interface must provide the behavior specified in the interface. This is useful when you need to enforce a specific set of methods across different classes without tying them to a common ancestor. Here's an example of an interface in Java. The drawable interface has a method draw, and the classes circle and square implement this interface, providing their own draw method implementations. This way, the behavior is defined by the interface but implemented by the individual classes. Now let's compare abstract classes and interfaces. Abstract classes can have both abstract and concrete methods, and they allow you to provide default implementations. On the other hand, interfaces define a contract for behavior, but the implementing classes must provide all method implementations. You can think of abstract classes as providing a blueprint, while interfaces provide a promise of behavior. So, when should you use an abstract class and when should you use an interface? If you have related classes that share common behavior, an abstract class is a good choice. If you need to define a common set of operations for unrelated classes, then an interface is more appropriate. Let's move on to an exercise. Your task is to create an abstract class called shape with an abstract method draw. Then create two derived classes, circle and rectangle, and implement the draw method in both classes. This will help you understand how abstraction simplifies your code and enforces structure. In summary, abstraction allows us to focus on the essential details and hide the complexity behind simpler interfaces. We can achieve abstraction through abstract classes and interfaces, both of which help structure our code in a way that is modular, flexible, and easy to maintain. That wraps up our session on abstraction. Make sure to practice the concepts we have covered today, as they are foundational to understanding OOP. Join us tomorrow for day 11, where we will dive into polymorphism. Thank you for your attention. Welcome to day 11, polymorphism. Today we will explore the fascinating world of compile time and runtime polymorphism in object-oriented programming. So, what exactly is polymorphism? The term comes from Greek meaning many shapes. In programming, it refers to the ability of a method or function to behave differently based on the type of object calling it. This concept is incredibly powerful because it simplifies code, making it more flexible. One interface can be used for different data types, allowing for a cleaner and more reusable code structure. There are two main types of polymorphism: compile time polymorphism, runtime polymorphism. Compile time polymorphism, also known as static polymorphism, which occurs at compile time. This is achieved through method overloading and operator overloading. Runtime polymorphism, also called dynamic polymorphism, which occurs during runtime and is achieved via method overriding. Let's dive into compile time polymorphism. Method overloading is a key concept here. This occurs when multiple methods have the same name but differ in their parameters, either in type or number. For example, in this class printer, we have two print methods, one for integers and one for doubles. The compiler decides which method to use based on the argument type at the compile time. Now let's talk about runtime polymorphism. This happens when a method in a base class is overridden by a method in a derived class. This allows the method to behave differently depending on the actual object type at runtime. For example, we have a base class animal with a virtual sound method. The derived class dog overrides the sound method to output bark. When we create an instance of dog, the sound method dynamically calls the method in the dog class, not the base animal class. Function overloading is a perfect example of compile time polymorphism. It occurs when multiple functions share the same name but have different parameter types or numbers. The compiler will determine which function to call based on the parameters passed to it. Method overriding is a feature of runtime polymorphism. It allows a method in a derived class to replace or override the behavior of the base class method. The base class method must be marked with a virtual keyword, and the derived class must use the override keyword. Virtual methods enable runtime polymorphism by ensuring that the method call corresponds to the actual object type, not the reference type. The decision of which method to call is made at runtime. This is called dynamic dispatch. Let's practice what we have learned. Create a base class shape with a virtual draw method and override this method in derived classes such as circle and rectangle. When you call the draw method on objects of these derived classes, we expect to see the appropriate output for each shape. Polymorphism brings several advantages. It enhances flexibility, allowing you to create objects of different types as objects of a common base class. It also promotes extensibility. New classes can be added without modifying existing code. Lastly, polymorphism improves code reusability, allowing the same method to be used across different classes and behaviors. To summarize, polymorphism allows one method to operate in multiple ways, simplifying and enhancing code flexibility. We have covered two main types of polymorphism: compile time, which is achieved through method overloading, and runtime, which is achieved through method overriding. The methods include improved the benefits include improved flexibility, code reusability, and extensibility. Next time we will explore another important concept in OOP: composition versus inheritance. We will learn when to use composition over inheritance to create more flexible and maintainable code. See you in the next session. Welcome to day 12 of our object-oriented programming course. Today, we will dive into a critical design decision, composition versus inheritance. We will explore both concepts and learn when it's better to use one over the other for more flexible and maintainable code. Today's objective is to help you understand the differences between composition and inheritance. You will learn when composition should be preferred choice over inheritance, ensuring better flexibility and modularity in your OOP designs. Let's start by understanding composition. Composition is a design principle where one object is composed of other objects to create complex functionality. It represents a has-a relationship. For instance, a library has books or a car has an engine. Composition offers flexibility by allowing you to create more adaptable and decoupled systems. The objects that contain other objects manage the lifetime of the contained objects. It also promotes code reuse as components can be used in different contexts. Now let's look at inheritance. Inheritance is a mechanism where one class, the child class, derives properties and behaviors from another class, the parent class. This represents an easy relationship, such as a dog being an element, a dog being an animal, or a car being a vehicle. Inheritance enables code reuse, where child classes inherit functionality from parent classes. However, it can create tight coupling between the child and parent classes. It also supports polymorphism, allowing for dynamic method overriding and more flexible behavior. So, when should you use composition over inheritance? Composition is ideal when the relationship is a has a relationship and when you need flexibility. It reduces dependency between classes and avoids creating deep inheritance hierarchies. Composition is also useful when you want to avoid the rigidity of inheritance. It allows for more modular systems, making your code easier to maintain and extend. On the other hand, use inheritance when the relationship is clearly an easy relationship. For example, a dog is an animal. Inheritance also Inheritance is also beneficial when you want to reuse code across multiple classes and take advantage of polymorphism. Let's look at an example. If we try to use inheritance in a library system, it may not make sense for the library to inherit from a building class. A library has books, not is a building. Instead, with composition, we can design a library as an object that contains books, members, and staff objects. Each of these components performs specific tasks, making the system more flexible and modular. Here's an example of the book class. It has attributes like title and author. and methods to get the book details. This can be easily reused in different contexts, such as in a library system or a bookstore. Next, we create the library class which holds books and members. We can add methods to manage the library, like adding a book or listing all available books. Here's how we can issue books. When a member requests a book, the system checks the books available in the library and issues the book if it's found. Composition offers several benefits. It provides flexibility and decoupling, meaning changes in one part of the system won't heavily impact others. It also avoids the pitfalls of deep inheritance hierarchies, making your code more maintainable. Now it's your turn. We will build a library management system. The library class will contain objects like book, member, and staff, each with specific responsibilities. Your task is to create a book. Your task is to create a book class with attributes like title and author, a member class with attributes like name and membership ID, and a library class to manage and issue books. Here's a member class example. It includes the member's name and membership ID and a method to borrow books from the library. You can customize this further to match your system's need. Here's the library class code, which manages the list of books and members. It allows you to add books, list them, and issue them to members. As we wrap up today's session, let me leave you with a quote by Peter Drucker. The best way to predict the future is to create it. Let this inspire you to design systems that are flexible and scalable. To summarize, composition and inheritance are both important concepts in OOP. Composition provides flexibility, decoupling, and modularity, while inheritance is best suited for clear, easy relationships and code reuse. Choosing between composition and inheritance depends on the context of your problem. Composition is a powerful tool for creating adaptable, maintainable code and is often the better choice for most design challenges. Thank you for joining today's lesson. I hope now I hope you now have a better understanding of composition and inheritance in object-oriented programming. If you have any questions or comments, feel free to ask. Welcome to day 13, practice day. Today we will focus on reviewing and reinforcing the key concepts we have learned so far, particularly in inheritance, abstraction, and polymorphism. This session will help you practice applying these concepts in real-world scenarios. Our learning goals for today include applying inheritance to build realistic class in hierarchies, demonstrating abstraction through the use of abstract classes and interfaces, practicing polymorphism by overriding methods and utilizing dynamic dispatch. For exercise 1, we will design a simple vehicle management system using inheritance. We will begin by creating a base class called vehicle, which will have properties such as brand, model, and year. These properties will be shared by all vehicles in our system. Next, we will create derived classes such as car, truck, and motorcycle. Each of these will inherit from the vehicle class and have specific attributes of their own. For example, the car class might have a seating capacity, while the truck class would have a payload capacity. We will also implement methods like start engine and stop engine and override them in the derived classes. Here's an example of the base vehicle class. It has public properties like brand, model, and year, and methods for starting and stopping the engine. Notice that we use the virtual keyword to allow these methods to be overridden in the derived classes. Now we move on to the derived classes. The car and truck classes inherit from vehicle. Each class has its own specific implementation of the start engine method. In the case of the truck class, the engine start message might be different from that of the car class, reflecting their unique characteristics. For exercise 2, we will implement abstraction in a library system. We will create an abstract class book which defines a method getDetails. Then we will create different types of books like textbook, novel, and magazine, which will each implement the getDetails method in their own way. Here's the abstract class book. It declares the pure virtual function getDetails, which must be implemented by any class that derives from it. The textbook class inherits from book and implements the getDetails method. The same is done by the novel class, but with a different message, showing how abstraction allows for flexible and dynamic behavior. In exercise 3, we will demonstrate polymorphism. We will create a shape hierarchy where different types of shapes such as circle and rectangle can calculate their area and perimeter. Polymorphism allows us to call these methods dynamically based on the actual object. Here we have the base class shape with two virtual methods, calculate area and calculate perimeter. These methods will be overridden in the derived classes to provide specific implementations for different shapes. In the derived classes such as circle and rectangle, we implement the methods to calculate the area and perimeter according to the respective formulas. Thanks to polymorphism, we can call these methods on a shape pointer, and the correct method will be called based on the actual object type. In exercise 4, we will explore abstract classes and interfaces. We will define an interface payment processor which will include methods like process payment and refund payment. Then we will create classes such as credit card payment and PayPal payment which will implement these methods. Here's the payment processor interface, which defines the methods for processing payments and issuing refunds. Any class that implements this interface must provide its own implementation of these methods. Now let's wrap up the session with a discussion. Reflect on the common challenges you might have faced during these exercises, and let's discuss how inheritance, abstraction, and polymorphism all contribute to building more flexible and maintainable systems. Before we finish, here are some practice tips. Focus on creating clear and concise class hierarchies. Emphasize the importance of polymorphism for writing reusable code. Experiment with real-world examples to solidify your understanding of these concepts. And finally, here's a motivational quote to inspire you. The best way to predict the future is to create it. Abraham Lincoln. Keep pushing forward and you will create a successful future for yourself as a programmer. Welcome to day 14 of our object-oriented programming course. Today we will recap key concepts from week 2 followed by a quiz, a coding exercise and a group discussion. Let's get started. Today's objective is to reinforce what we have learned in week 2, focusing on core OOP concepts. We will cover inheritance, method overriding, abstraction, polymorphism, and composition. After the recap, you will have a quiz to test your understanding, a coding exercise to put your skills to practice, and an opportunity for a group discussion to clarify any doubts. Let's begin with a quick recap of the key concepts we have covered so far in week 2. Inheritance. The ability to create new classes based on existing ones, allowing for code reuse and extension of functionality. Method overriding, changing the behavior of methods in a derived class. Abstraction, hiding unnecessary details and exposing only the essential features of an object. Polymorphism, the ability to call the same method on different objects, each responding in their own way. Composition, a design principle where a class contains references to objects of other classes, representing a has-a relationship. Let's dive into inheritance. In OOP, inheritance allows you to create new classes based on existing ones. For example, a manager class can inherit from an employee class, reusing its functionality while adding new behavior. There are different types of inheritance like single, multi-level, and hierarchical inheritance, which enable you to organize and extend your classes efficiently. Next, we have method overriding and the super keyword. Method overriding allows a derived class to provide its own implementation of a method that is already defined in the base class. Using the super keyword, we can call methods from the parent class, enabling us to extend or modify the inherited behavior. For example, a car class might override a start method from the vehicle class to include specific functionality. Moving on to abstraction, which involves hiding the complex implementation details of a class while exposing only the necessary information. An abstract class in OOP provides a blueprint for other classes, defining methods that must be implemented by derived classes. For example, a payment class would define a method for processing payments, while different payment methods like credit card or PayPal implement their own version of the method. Now let's discuss polymorphism. Polymorphism allows objects to respond to the same method in different ways, making your code more flexible and reusable. There are two types: compile-time polymorphism, which includes method overloading, and runtime polymorphism, which involves method overriding. This concept is essential for writing clean and scalable code. Next, we will talk about composition versus inheritance. Composition involves creating objects that contain other objects representing a hazard relationship. It's often preferred over inheritance when you need to avoid tight coupling between classes. For instance, a library class might contain a collection of book objects rather than inheriting from the book class. Composition is a powerful tool for building flexible systems. It's quiz time. Let's test your knowledge on the concepts we have covered. Question 1. Which of the following best defines inheritance in OOP? A way to protect data, a method of creating new classes from existing ones, a mechanism to execute methods, a way to represent real-world objects. Question 2. What does method overriding allow in OOP? Modifying the base class constructor, changing the method behavior in a derived class, calling methods from multiple classes, and D. None of the above. Now it's time for a coding exercise. Your task is to create a class hierarchy for shapes, starting with an abstract shape class and adding derived classes like circle and rectangle. Each class should implement its own version of the draw method. Use polymorphism to call the draw method on different shape objects. This will give you a chance to apply inheritance, method overriding, and polymorphism. Let's pause for a group discussion and Q&A. If you have any questions about the quiz or the coding exercise, now it's time now it is the time to ask. We will go over any concepts that need clarification and share any insights or challenges you encounter. This is a great opportunity to discuss and deepen your understanding. Before we wrap up, let's do a final recap. Inheritance allows us to create new classes based on existing ones. Method overriding lets us change method behavior in derived classes. Abstraction simplifies complex systems by hiding unnecessary details. Polymorphism lets us use the same method in different ways. Composition provides a flexible alternative to inheritance for creating relationships between objects. Remember, mastering these concepts will give you a solid foundation for writing modular, reusable, and scalable code in any OOP language. For further learning, here are some excellent resources. Books like Design Patterns and Refactoring can dive, help you dive deeper into OOP. Online platforms like LeetCode, HackerRank, and CodeWars are great for practicing your skills. Websites like Tutorials Point and Geeks for Geeks offer in-depth articles on OOP concepts. Keep exploring these resources to continue improving your understanding of OOP. Lastly, here's an optional assignment. Design a class hierarchy for a school management system with classes like person, teacher, student, and course. Implement inheritance, polymorphism, and composition in your design. This will give you hands-on experience in applying all the OOP concepts we have covered. Welcome to this session on solid principles in object-oriented programming. Today, we will explore the 5 essential design principles that make software maintainable, scalable, and extensible. First, let's introduce SOLID. SOLID is an acronym for 5 design principles that help you write better software. By focusing on making our code cleaner, reusable, and decoupled, we can achieve higher quality and more maintainable systems. Our first principle is a single responsibility principle, or SRP. The key idea here is that a class should have only one reason to change. This means that a class should only have one responsibility. For example, imagine a class that handles both customer data and sending notifications. It's better to separate these responsibilities into two different classes. This way, each class is easier to maintain and test. Next is the open or closed principle, or OCP. This principle states that classes should be open for extension but closed for modification. In simple terms, you should be able to add new features without changing existing code. For example, instead of modifying a class every time a new feature is needed, we use inheritance and polymorphism to extend functionality while keeping the original code untouched. Moving on to the Liskov substitution principle, or LSP, this principle tells us that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. If a subclass does not behave as expected when substituted for its superclass, it can cause issues. So, we need to ensure that derived classes maintain the expected behavior. Now, let's look at the interface segregation principle, or ISP. The idea here is that clients should not be forced to depend on interfaces they do not use. This means we should split large interfaces into smaller, more specific ones. By doing so, we avoid creating unnecessary dependencies and make our system more focused and lightweight. The last of the 5 principles is the dependency inversion principle, or DIP. According to this principle, high-level modules should not be should not depend on low-level modules. Both should depend on abstractions. This promotes loose coupling between components and improves maintainability. In practice, we achieve this by using dependency injection to pass in abstractions instead of concrete implementations. Now that we know the principles, let's look at how to refactor a poorly designed class. For instance, let's consider a user manager class. This class currently handles multiple responsibilities like storing user data, validating it, and sending notifications. We can refactor this class by separating these concerns into different classes. Here's how we can refactor the user manager class to follow solid. We will create separate classes for storing user data, validating user data, and sending emails. We will use interfaces to allow easy extension and dependency injection to reduce tight coupling. By doing this, our code will be more modular, flexible, and easier to maintain. Let's take a look at the refactored code. We now have a user storage class, a user validator class, and an email service class. Each of these classes has a single responsibility. The user manager class uses dependency injection to interact with these services. This is a simple yet effective example of applying solid principles to improve our design. So, what are the key takeaways from today's session? First, remember that SRP helps you separate concerns. OCP encourages you to extend, not modify. LSP ensures that subclasses behave as expected. ISP teaches us to create small, focused interfaces. And finally, TIP promotes loose coupling between components through abstractions. In conclusion, solid principles are essential for building clean, maintainable, and scalable systems. By applying these principles, we can improve our design, reduce bugs, and make our code easier to maintain over time. So, next time you are designing a system, consider these principles to improve the overall quality. That wraps up today's session on solid principles. I hope you found it helpful. Now, I would love to hear your thoughts or answer any questions you might have. Let's open the floor for discussion. Welcome to today's session on Design Patterns Overview. In this session, we will explore the key categories of design patterns: creational, structural, and behavioral, and understand how these patterns can help improve your software design and development practices. So, what exactly are design patterns? Design patterns are reusable solutions to common problems that arise during software development. They provide best practices that have been proven to work in various scenarios, helping us write cleaner, more maintainable code. By using design patterns, we can improve code readability, make our software more flexible, and reduce complexity over time. Design patterns can be categorized into three main types: creational, structural, and behavioral. Each category addresses different aspects of software development. Creational patterns focus on the process of object creation. Structural patterns deal with how objects and classes are organized and related, and behavioral patterns help define how objects interact with each other. Let's take a closer look at these categories. Creational patterns abstract the process of object creation to make it more flexible and dynamic. Structural patterns help in composing objects and classes into larger structures, enabling more efficient organization. Lastly, behavioral patterns focus on communication between objects and the delegation of tasks, helping achieve well-organized object interactions. Let's dive into the first creational pattern, the singleton pattern. The singleton pattern ensures that a class has only one instance and provides global access to it. This is useful when we want to control access to a resource like a database connection, ensuring that there's only one instance of a connection throughout the entire application. Here's a quick look at the code for the singleton pattern. As you can see, the class has a private constructor, preventing instantiation from outside the class. It also contains a static method getInstance, which checks if the instance already exists. If not, it creates one and returns it. This ensures that only one instance of the class is created, regardless of how many times the getInstance method is called. Next, we have the factory pattern. The factory pattern is used to create objects without specifying the exact class of object that will be created. It abstracts the object creation process, which helps in promoting loose coupling. This pattern allows us to create different types of objects depending on specific conditions or parameters without changing the client code that uses the factory. Let's take a look at a simple factory pattern example. Here we defined an abstract button class with a render method. Then we have two concrete classes, Windows button and Mac OS button, that implement the render method differently for their respective platforms. The factory will be responsible for determining which button to create. In the next part of the factory pattern, we define the button factory class. The createButton method in this class takes a string parameter OS type, and based on its value, it creates and returns either a Windows button or a Mac OS button. This demonstrates how the factory pattern helps in deciding which class to instantiate without explicitly specifying it in the client code. Design patterns are incredibly important because they provide a common vocabulary for developers. They help us solve complex design patterns in a more structured and efficient manner. By using design patterns, we adhere to best practices, which leads to more maintainable, scalable, and flexible software in the long run. In our next session, we will dive deeper into specific patterns like singleton and factory, and we will have the opportunity to implement them in real world scenarios. We will also explore more advanced patterns and how to help apply them effectively in different situations. Stay tuned for more hands-on practice in upcoming sessions. Welcome to day 17 of our course on creational design patterns. Today we will be diving deep into the singleton pattern, a key concept in object-oriented design that ensures a class has only one instance. Creational design patterns focus on how objects are created. These patterns abstract the instantiation process, providing flexibility and control over object creation. One of the most well-known creational patterns is the singleton pattern, which ensures that a class has only one instance throughout the application. The singleton pattern guarantees that a class has only one instance and provides a global access point to that instance. This pattern is especially useful when you want to manage shared resources across your application, like a database connection or configuration settings. Consider using the singleton pattern when you need global access to a single instance of a class. It's perfect for managing shared resources such as logging and database connection, where you want to ensure only one instance exists across the application. There are three key characteristics of the singleton pattern: private constructor, static instance, global access point. In private constructor, the constructor is private to prevent direct instantiation from outside the class. Static instance: a static variable holds the instance of the class, ensuring that only one instance exists. Global access point: a public method, typically getInstance, provides access to the instance, ensuring that it's used consistently throughout the application. Here's a simple implementation of the singleton pattern in C++. The class has a private constructor and a static instance variable. The getInstance method ensures that the instance is created only once and returns the single instance when needed. In the client code, we can see how the singleton instance is accessed. Even if we call getInstance multiple times, both S1 and S2 will point to the same instance of the singleton class, providing that only one instance exists. The singleton pattern has several advantages. Control over object creation. It ensures only one object is created. Global access. The instance is accessible globally, making it easy to share across different parts of the application. Memory efficiency. Only one instance is created, reducing memory usage compared to multiple instances of the same class. Other advantages include centralized object management. The the management of the object is centralized, making it easier to maintain and manage. Flexible initialization. The instance can be lazily initialized, meaning it will only be created when needed. Consistency. Consistency ensures that the state of the object is consistent across the application as only one instance is used. While the singleton pattern has many benefits, it also comes with disadvantages. Global state, hard to extend, and concurrency issues are the disadvantages. Global state introduces global state which can lead to difficulties in testing and debugging. Hard to extend, singleton classes are often difficult to subclass or extend. Consistency issues arises in multi-threaded environment. Creating the instance Creating the instance could lead to race conditions if not handled properly. In multi-threaded environments, the singleton pattern can lead to issues where multiple threads try to create the instance simultaneously. To solve this, we synchronize the getInstance method using locks or mutexes, ensuring that only one thread can create the instance at a time. Real-world use cases for the singleton pattern include logger class, database connection, configuration settings. Logger class ensures a single instance for logging across the application. Database connection manages a shared database connection. Configuration settings is used for storing and managing global configuration settings in one place. Now it's your turn. Try implementing a singleton pattern for a thread pool class. The goal is to ensure only one instance of the thread pool is created and shared across your application. Make sure to handle thread safety as well. To summarize the key takeaways, the singleton pattern ensures that only one instance of a class is created. It provides a global access point to that instance. It's ideal for managing shared resources like logging, database connections, and configuration settings. Be aware of potential issues such as global state and concurrency problems. What's next? We can you can explore other creational design patterns like the factory method and abstract factory. Try implementing the singleton pattern in your own applications and practice identifying situations where this pattern can be applied. Welcome to this presentation on creational design patterns, specifically focusing on the factory pattern. In this session, we will explore the factory pattern and understand its role in object-oriented design. By the end, you will know how to apply it in your own projects. Let's begin with an introduction to the factory pattern. This pattern is a creational design pattern used to abstract the process of creating objects. Instead of directly instantiating objects, we delegate the creation to a factory class, which decides which specific class to instantiate. This allows flexibility and decouples the client code from the class being created. The factory pattern is especially useful when we need to create objects without knowing the exact type, or when the object creation process is complex. It centralizes the logic of object creation, making the code easier to maintain and modify. It's also ideal when you want to keep your client code decoupled from specific classes, enhancing the flexibility of your system. There are three main types of factory patterns. The simple factory pattern, where a single function handles object creation. The factory method, where an abstract method is defined for creating objects and concrete subclasses implement this method. The abstract factory, which provides a family of related methods for creating families of objects. Now let's look at some key benefits of using the factory pattern. First, it helps with decoupling. By abstracting the object creation logic into a factory, the client code no longer needs to know how objects are instantiated. Second, it offers flexibility as the factory can decide which type of object to create at runtime based on conditions or configurations. Continuing with the benefits, the factory pattern also provides centralization of object creation. This makes maintenance easier since changes to object creation only need to be made in one place. Lastly, it promotes extensibility. Adding new object types to your system is easier because you only need to extend the factory without altering the client code. Let's look at an example of how the factory pattern works in practice. Imagine we need to create buttons for different platforms such as Windows and Mac OS. First, we define a button interface that will be implemented by different button types for each platforms like Windows button and Mac OS button. Next, we create concrete classes for each platform's button. For example, a Windows button class would implement the render method to display a Windows specific button, and a Mac OS button would do the same for Mac OS. Now we create the factory button. This factory decides which button to instantiate based on the operating system type. In this case, the factory will create a Windows button if the OS is Windows and a Mac OS button if the OS is Mac OS. Finally, in the client code, we can call the button factory to create the correct button type based on the operating system. This way, the client code does not need to know about the specific classes of the buttons. It simply requests the button it needs and the factory handles the rest. To summarize, the factory pattern is a powerful tool in object-oriented design. It abstracts the object creation process, decouples client code from specific classes, and makes your system more flexible, maintainable, and extensible. It's especially useful in scenarios where the object creation logic is complex or subject to change. Consider using the factory pattern when you need to create different types of objects dynamically without knowing the exact class beforehand. It's also beneficial when object creation is complex or conditional, or when you need to create creation centralize creation logic. This pattern ensures that your client code remains decoupled from specific implementation classes. To wrap up, here's an exercise for you. Try implementing a button factory that can create a Windows button, Mac OS button, and a Linux button based on the operating system type. This will give you hands-on experience with the factory pattern and deepen your understanding of its real-world applications. Thank you for your time. I hope this presentation has helped you understand the factory pattern and how it can be used to improve the flexibility and maintainability of your object-oriented systems. Happy coding! Welcome to day 18 of our course on design patterns. In today's session, we will cover two essential structural design patterns, the adapter pattern and the composite pattern. Let's get started. Structural design patterns focus on how classes and objects can be combined to form larger, more complex structures. These patterns aim to simplify relationships between components and ensure that systems are flexible and scalable. Today, we will focus on two such patterns, adapter and composite. The adapter pattern allows objects with incompatible interfaces to work together. Essentially, it acts as a bridge, converting an interface into another that the client expects. This pattern is typically used when integrating legacy systems or third-party libraries that don't match the expected interface. Imagine you are integrating an old payment system into a modern e-commerce platform. The old system uses a different interface than the one expected by the platform. By using the adapter pattern, you can convert the old system's interface into the one expected by the new system, making integration seamless. Here we define the adaptee, which is the old payment system. This system has its own way of making payments, but it does not match the expected interface of the modern platform. Our goal is to adapt this interface to fit the new system. Now we define the target interface, which is what the client expects. This interface contains the method that the new system will use to process payments. Our adapter will make sure that the old system conforms to this interface. This is where the adapter comes in. The payment adapter class takes the old payment system and adapts it to the expected interface. By implementing the target interface, the adapter allows the old system to work seamlessly within the new system. The key components of the adapter pattern are the adaptee, which is the old system, the target, which is the expected interface, and the adapter, which converts the adaptee's interface to match the target. This pattern helps integrate legacy systems without altering their internal code. For the exercise, you will implement an adapter for an old payment gateway. This will give you hands-on experience in adapting legacy systems to a new unified interface. The composite pattern allows us to treat individual objects and compositions of objects in a uniform way. It's especially useful when dealing with tree-like structures, where both single objects and groups of objects need to be treated the same way. Think about a file system where directories contain both files and other directories. The composite pattern allows us to treat both individual files and entire directories as components, simplifying the management of this hierarchical structure. Here we define the component class, which is the base class for both individual objects like files and composites like directories. The component class defines a common interface for all objects in the tree structure. In this step, we define the leaf classes such as circle and square. These are the individual objects that we want to treat uniformly. Each leaf class implements the common interface defined in the component class, allowing them to be treated the same as composite objects. Next, we create the composite class, graphic group. This class is capable of holding multiple graphic objects, including both individual leaf objects and other composite objects. By implementing the same interface, the composite class can treat all of its components uniformly. The main concepts of the composite pattern are the component class, which defines the common interface, the leaf class, which represents individual objects, and the composite class, which groups objects together. This pattern allows us to manage complex hierarchical structures easily. The composite pattern provides several advantages. It allows flexibility as new objects can be added without altering the existing structure. It also simplifies the handling of hierarchical structures, making the code easier to maintain and extend. In this exercise, we will create a composite structure for a menu system. This system will allow both individual menu items and nested menus to be treated as components. demonstrating how the composite pattern can be applied in a real-world scenario. Let's compare the adapter and composite patterns. While the adapter pattern is focused on converting interfaces to integrate incompatible systems, the composite pattern simplifies the management of hierarchical structures by creating both individual and composite objects uniformly. To summarize, the adapter pattern helps integrate incompatible interfaces without changing the underlying code, while the composite pattern makes it easier to work with hierarchical structures by treating individual and composite objects uniformly. Be sure to practice these patterns to master their implementation in your projects. That brings us to the end of the presentation. Do you have any questions or would you like to discuss any of the concepts covered today? Feel free to ask about the adapter or composite patterns or share any challenges you encountered in the exercises. Welcome to the presentation on behavioral design patterns, focusing on the observer and strategy patterns. Let's dive into these crucial design patterns and explore how they help improve object interaction and flexibility in software design. Behavioral design patterns are all about how objects interact and communicate with each other. These patterns define the way objects should collaborate and share responsibilities, ensuring effective communication and interaction within the system. There are several behavioral patterns, with the observer and the strategy patterns being key examples. The observer pattern helps notify multiple objects when a change occurs, while the strategy pattern allows for selecting a specific algorithm at runtime. These patterns aim to simplify object interaction, ensuring better scalability and maintainability. The observer pattern is a design pattern where an object called the subject notifies its dependent objects known as observers whenever its state changes. Think of it like a news agency that notifies all its subscribers about breaking news events. This pattern is commonly used in notification and event handling systems. In the observer pattern, there are several key components. The subject, which maintains a list of observers and notifies them of any state changes. The observer, which defines an interface for receiving updates. The concrete subject, which implements the subject interface and sends updates. The concrete observer, which implements the observer interface and reacts to the updates. The workflow of the observer pattern involves three key steps: attach, update, react. Attach observes register themselves with the subject. Update, the subject changes its state and notifies all registered observers. React, observers receive the updates and perform necessary actions based on the new information. Here's a simple example. Consider a notification system where users subscribe to receive updates on stock prices or news events. When an event such as a price change occurs, all subscribers are automatically notified. This is the essence of the observer pattern. The strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. This pattern allows the algorithm to be selected at runtime based on the specific context. For example, in a payment system, a user can choose between different payment methods such as credit card, PayPal, or cryptocurrency. The strategy pattern consists of three main components: the strategy interface, which defines a family of algorithms; the concrete strategy, which implements a specific algorithm; the context, which maintains a reference to a strategy object and calls the algorithm defined by the strategy. The workflow of the strategy pattern involves three main steps. Set strategy. The context sets a specific strategy for its operation. Execute. The context delegates the execution of the strategy to the selected algorithm. Switch. The strategy can be dynamically switched based on the context, allowing flexibility in the system's behavior. Let's look at a real-world example: a payment system where users can choose from multiple payment methods such as credit card, PayPal, or cryptocurrency. At runtime, the user selects a strategy and the system processes the payment accordingly. This dynamic selection of strategies is the essence of the strategy pattern. In this exercise, our goal is to implement an observer pattern for a notification system. The task is to create a system where users can subscribe to notifications and receive updates whenever there's a change in the system state, such as an event or status update. Let's take a look at the code implementation of the observer pattern. First, we define the observer interface, which includes an update method that will be called when the subject's state changes. Similarly, we define the subject interface, which includes methods for adding, removing, and notifying observers. In the next part of the implementation, we define the concrete subject class, which implements the subject interface. The notification system class maintains a list of observers and notifies them when the state changes. It also includes a set message method to trigger the notifications. Now let's look at the concrete observer class. The user class implements the observer interface and reacts to the updates by printing a message when it receives a notification. In this case, the update method displays the received message on the console. Finally, in the main function, we test the notification system. Users Alice and Bob subscribe to notifications and receive a message when the system state changes. We also demonstrate how an observer can be removed from the system so it no longer receives updates. In conclusion, the observer pattern helps decouple the subject and observers, making it easy to add or remove observers dynamically. The strategy pattern, on the other hand, promotes flexibility by allowing algorithms to be switched at runtime, reducing conditional logic and encapsulating behavior in separate strategies. Thank you for your attention. I now open the floor for any questions you might have about the observer and strategy patterns or any related topics discussed today. Hello and welcome to this presentation on UML diagrams. In this session, we will dive into the concepts of class and sequence diagrams, two essential tools in the unified modeling language used for system design. Let's get started. UML, or Unified Modeling Language, is a standardized way to visually represent the design of a system. It helps developers, designers, and business analysts communicate more effectively by providing a common visual language. UML covers several types of diagrams, including class diagrams, sequence diagrams, use case diagrams, and activity diagrams, each serving a unique purpose in system modeling. Class diagrams are used to represent the static structure of a system. They illustrate the system's classes, their attributes, methods, and the relationships between them. A class diagram serves as a blueprint for objects, showing how they interact and are related within the system. Let's break down the key components of a class diagram. Class diagrams contain several types of relationships. First, we have generalization or inheritance, which is represented by a line with a triangle pointing to the parent class. For example, a manager is a type of employee. Next, there's dependency, which is a dashed line showing that one class depends on another. Finally, multiplicity, which describes how many instances of one class are associated with another, like how one customer can place multiple orders. Let's look at an example of a class diagram in the context of an e-commerce system. Here we have several classes: a customer, a product, an order, and a payment. Each class has attributes like the customer's name or the product's price, and methods such as an order or processing a payment. These classes interact with each other to complete the e-commerce workflow. In our e-commerce system, there are key relationships between these classes. A customer can place many orders, forming a one-to-many relationship. An order can have many products, which is a many-to-one relationship, and each order has a corresponding payment, forming a one-to-one relationship. These relationships are fundamental to the operation of an e-commerce platform. Moving on to sequence diagrams, while class diagrams represent static structures, sequence diagrams focus on dynamic interactions between objects over time. They show how objects communicate with each other through a series of messages or events. Let's take a closer look at the components of a sequence diagram. Here's an example of a sequence diagram for an e-commerce order process. First, the customer requests to view products. The system responds by sending the available products. Then the customer selects a product and places it in the cart. Afterward, the system processes the order and the customer proceeds to payment. The payment service processes the payment, and finally, the system updates the order status. This this diagram shows the flow of messages between the entities involved. Now let's practice creating UML diagrams. Imagine you are designing a library system. We have several classes: a book, a member, a librarian, and a library. Each class has its own attributes and methods, such as a member's ability to borrow books or a librarian's role in adding and removing books. Your task is to draw the UML diagram for this system. In the library system, a member can borrow multiple books, forming a one-to-many relationship. The librarian manages both the books and the members, ensuring smooth operations. The library itself contains many books and members, showing how the system is organized. Let's visualize the borrowing process in a library system with a sequence diagram. First, the member searches for a book. The library checks if the book is available. If it is available, the member borrows the book. The librarian records the transaction and the member receives the book. This diagram shows the sequence of interactions that occur when a member borrows a book. To summarize, UML diagrams are essential tools for visualizing the structure and behavior of a system. Class diagrams provide a static view showing classes and their relationships, while sequence diagrams focus on the dynamic interactions over time. We have also looked at a practical example and an exercise to help solidify these concepts. That concludes the presentation. If you have any questions or would like to discuss any of the concepts further, feel free to ask. I would be happy to clarify anything you need. Hello everyone and welcome to today's session on design patterns and principles. Today we will be solving problems using design patterns and our focus will be on designing a notification system. Let's dive into the practical aspects of how design patterns can be applied to real-world challenges. In this video, I will be guiding you through the process. Before we jump into the system design, let's first look at the objectives of today. The goal is to reinforce our understanding of design patterns and principles through hands-on practice. We will solve problems involving common patterns like singleton, observer, and factory. In addition, we will review the solid principles and apply them while designing a real-world system, our notification system. Let's now move to our problem scenario. Designing a notification system. The system needs to send messages through multiple channels like email and SMS. It must be flexible, scalable, and extensible, ensuring we can easily add new channels in the future. For example, if we want to add push notifications or WhatsApp, we should be able to integrate them without much hassle. The system should also handle large-scale notifications and future notification types like urgent or promotional messages. As we approach the design, we need to consider a few key factors. First, flexibility is crucial. New notification channels should be easy to add without changing existing code. Second, scalability. Our design must support handling a large number of notifications. And third, extensibility. We should be able to add new types of notifications in the future without disrupting the system. Now let's discuss the key design patterns we will use to build our system. The strategy pattern will allow us to choose different notification channels dynamically. The observer pattern is useful when we need to notify multiple users about events. The factory pattern will help us create instances of different notification channels based on user preferences. And finally, the singleton pattern will ensure that we have a single shared resource for global configurations like API keys or logging. Let's start with the strategy pattern. This pattern allows you to define a family of algorithms, in our case, notification channels. The benefit of the strategy pattern is that it enables dynamic switching between different notification channels like email, SMS, or push notification during runtime without altering the core logic of the system. Next, we have the observer pattern. In this pattern, we use it when our system needs to notify many users about specific events, such as sending updates. The observer pattern ensures that when one object or subject changes its state, all dependent objects are notified and updated automatically. Moving on to the factory pattern, which is useful for creating objects without specifying the exact class of object to be created. For our notification system, the factory pattern will decide which notification channel to create, like email or SMS, based on input from the user or system configuration. Now let's discuss the singleton pattern. This pattern ensures that a class has only one instance and provides a global point of access to it. For our system, we can use singleton to control shared resources like the configuration of the system or access to a logging services. Now let's begin designing the notification system. The central component is the notification object, which holds the message and the type of notification. We will create a notification channel interface, which will be implemented by concrete classes like email channel and SMS channel. The notifier class will handle sending notifications to the chosen channel. Step 1 is to create the notification channel interface. This interface defines the method send notification, which will be used by concrete notification channels like email or SMS. By using an interface, we ensure that we can easily add more channels in the future without changing the code logic. In step 2, we implement the concrete channel classes. For instance, the email channel class will implement the send notification method to send an email, and similarly the SMS channel class will handle sending text messages. Each class will have its own implementation of the send notification method. Next, we create the notifier class. This class is responsible for sending the notification. It holds a reference to a notification channel and calls the send notification method on it. The notifier class allows us to switch between different notification channels without modifying the core notification logic. In step 4, we implement the factory pattern. The notification factory class will create instances of different notification channels based on input. This pattern helps us decouple the logic of creating channels from the rest of the system, allowing us to add new channels easily. Now let's put everything together. In the main function, we first create a channel type like email. We then use the notification factory to create the appropriate channel. Finally, we use the notifier class to send the notification through the selected channel. This approach ensures our system is flexible, scalable, and easy to extend. So, what are the benefits of our system? First, it provides flexibility by allowing us to add new notification channels without changing existing code. Second, it scales well to handle a large number of notifications. And third, it's extensible, allowing us to easily add more notification types or features in the future. To wrap up, here are some additional practice challenges for you. You can modify the system to add features like retrace logging, or rate limiting. Retries logging, or rate limiting. Retries logging or rate limiting. You can also explore using the decorator pattern to dynamically add features like error handling. And if you are feeling adventurous, try implementing notifications using multi-threading or queues for improved performance. That concludes our session on design patterns and principles applied to the notification system. I hope you find this session useful and learned how to apply design patterns in real-world scenarios. Thank you for your attention. Welcome to today's session on exception handling in C++. This is day 22 of our object-oriented programming course, where we will dive into the concept of handling errors, ensuring smoother program execution, and better user experiences. Let's start by understanding what exceptions are. An exception is an event that disrupts the normal flow of a program. They can happen during execution and may be caused by errors like division by zero or invalid input. There are two types of exceptions: logical errors, which are mistakes in your program's logic, and runtime errors, which occur while the program is running, such as accessing invalid memory. Why should we handle exceptions? There are several key reasons. First, handling exceptions helps with error recovery, preventing your program from crashing. It allows the program to continue running after an error occurs. Second, it provides useful feedback to users, helping them understand what went wrong. Third, it keeps your code clean and organized by isolating error-prone code in try-catch blocks. Lastly, it ensures proper resource management like choosing files or releasing memory, like closing files or releasing memory when an error occurs. Next, let's look at the try-catch blocks. These are the fundamental constructs used for exception handling. The try block contains the code that may throw an exception, while the catch block catches the exception and handles it. This separation helps maintain the flow of the program even when something unexpected happens. Here's the syntax of try-catch block. In C++, the try block is followed by one or more catch blocks. The catch block catches exceptions thrown in the try block. In the example, we catch exceptions of type std::: exception and print the error message using the what method. This allows us to gracefully handle errors instead of letting the program crash. Let's look at a practical example. Catching a division by zero error. In the code, if the denominator is zero, we throw a std::: logic error. This error is then caught by the catch block, which prints the error message. This is a simple way to handle one of the most common runtime errors. Now let's talk about custom exceptions. While standard exceptions like std::: exception are useful, sometimes you may want to create exceptions specific to your program's need. A custom exception is a user-defined class that inherits from std::: exception, giving you more control over error handling in particular situations. To create a custom exception, we define a class that inherits from std::: exception and overrides the what method. This method returns a custom error message when an exception is thrown. In this case, our custom exception, invalid exception, returns the message invalid input encountered. Here's an example of how to throw and catch our custom exception. In the try block, we throw an instance of invalid input exception. The catch block then catches this exception and prints the custom error message using the what method of the exception class. Now let's move on to an exercise. In this exercise, we will create a custom exception to handle invalid input in a banking application. The goal is to catch errors like negative deposit amounts or incorrect account numbers before they can cause problems in the system. To start, we define the custom exception class invalid input exception. This class overrides the what method to return a specific error message whenever invalid input is encountered. Let's see how this fits into the banking app. Here's a full example of our banking app. The bank account class contains methods for depositing and withdrawing money. If the user enters an invalid amount like a negative value, the custom exception invalid input exception is thrown. The exception is then caught and the appropriate message is displayed. Now we run the banking app with some test cases. In the first test case, we try to deposit a negative amount which triggers the invalid input exception. In the second test case, we try to withdraw more money than available, which again triggers the exception. The program handles both errors gracefully without crashing. To recap, exception handling helps us manage errors effectively in C++ by using try-catch blocks. We can also create custom exceptions to handle specific errors that arise in our program. These tools help ensure our programs run smoothly, even when unexpected events occur. Here are some best practices for exception handling. First, we use exceptions sparingly, only for true exceptional situations. Second, catch different types of exceptions separately for more specific handling. Lastly, always ensure proper cleanup of resources like files or memory, even if an exception is thrown. For further practice, try implementing other types of exceptions like std::: out of range and add more complex error handling logic to the banking app. You can also expand the app to include file operations or network related exceptions. That concludes the presentation on exception handling in C++. Do you have any questions or would you like to discuss any of the concepts in more detail? Welcome to day 23, where we will be diving into file handling and object-oriented programming. Today, we will explore how to read and write files using objects, as well as the concepts of serialization and deserialization. File handling in object-oriented programming, or OOP, involves reading from and writing to files using object-oriented principles. This process allows you to process data between program executions, making it possible to save complex objects and later retrieve them, even after your program has ended. Two key concepts in file handling are serialization and deserialization. Serialization is the process of converting an object into a storable format such as text or binary. Deserialization, on the other hand, is the reverse process, converting that stored data back into an object. Common formats for serialization include JSON, XML, and binary files. Serialization and deserialization are essential when it comes to saving and loading object data. Serialization converts the object into a byte stream or text format so it can be easily written to a file. Deserialization reads the byte stream or text back from the file and reconstructs the object, allowing you to use it as if it had never left your program. When writing objects to files, the object must first be serialized into a format that can be saved. This serialized data is then written to a file. In real-world applications, this can be useful for storing user data, configuration settings, or game progress in formats like JSON or binary files. Here's an example in C++ of how you can serialize a student object and save it to a text file. We defined a student class with attributes like name, age, and roll number, and then we serialized those attributes to a file using the serialize method. Just as we write objects to files, we can also read them. To do this, the data stored in the file needs to be deserialized. This process converts the stored data back into an object that can be used in our program, making it possible to restore program states or load user data. In this example, we read from a file and deserialize the data into a student object. The deserialize method reconstructs the object by reading the stored values from the file. After deserialization, we can access the student's detail and use them in our program. For the exercise, we will create a program that allows us to save a list of students to a file and later load it back into our program. This will involve serializing and deserializing a collection of student objects, enabling us to store and restore data across different sessions of the program. Here's the solution outline. We first defined a student class with methods for serialization and deserialization. Then we create a student list class to manage multiple students. This class will have methods to save the list to a file and load it back. Finally, we implement these functionalities in the main program. Let's walk through the code. The student class handles the serialization and deserialization of individual students. The student list class manages a collection of students, providing methods to save the list to a file and load it from a file. The main function demonstrates how to add students, save them to a file, and later load and display them. To summarize, serialization allows us to convert objects into a storable format, while decentralization allows us to retrieve objects from that format. File handling in OOP makes it possible to process data, ensuring that objects can be saved and restored even after a program ends. File handling is a crucial aspect of many real-world applications, especially when you need to maintain object state or save user data. By using serialization and deserialization techniques, we can easily store and retrieve data, making our applications more robust and efficient. Welcome to today's presentation on object-oriented programming in real-world applications. In this session, we will explore how OOP is used in large-scale systems and its role in industries such as banking, e-commerce, game development, GUI frameworks, and web development. Object-oriented programming or OOP is a design paradigm that models real-world entities as objects. It helps in managing complexity and maintaining large systems by dividing them into smaller, more manageable parts. By using OOP, developers can enhance code reusability, modularity, and flexibility. Key OOP features like inheritance, polymorphism, and encapsulation are vital in creating scalable and maintainable software solutions. Let's look at a banking system example. In an OOP-based banking system, we can model entities such as accounts, customers, and transactions as objects. For instance, the base class could be account with specialized classes like saving account and current account inheriting from it. Polymorphism will also useful here. Methods like deposit and withdraw can behave differently based on the type of account. This approach simplifies maintenance and allows easy extensions of the system. Next, let's im- let's let's examine an e-commerce system. In this system, we could have classes like product, order, and customer. These classes represent key entities in the e-commerce domain. Inheritance is useful for distinguishing between different user types such as customers and admins. Polymorphism allows actions like payment processing to differ based on the method chosen, such as credit card or PayPal. This structure supports scalability and flexibility in e-commerce applications. In this continued example of an e-commerce system, we see how various components interact. A cart class may manage adding and removing products, while different user roles like guest and admins interact with the system differently. For example, only an admin would have access to actions like deleting users or managing inventory. This illustrates the power of OOP to create a robust, scalable system where components are reusable and maintainable. Now let's explore an online learning platform. In this example, the system could have classes like course, student, instructor, and lecture. Inheritance allows us to have different types of users like students and instructors, both inheriting from a base user class. Polymorphism comes into play when methods like login have different implementations for each user type. This allows a unified approach to user management while accommodating different user behaviors. Moving on to game development, OOP plays a crucial role in designing game entities like players, enemies, and items. Each game object can be treated as an object with properties such as health, score, and position. For instance, you could have an enemy class with subclasses like zombie or alien. each implementing different attack behaviors using polymorphism. This structure is, also allows easy management and extension of game features as the game evolves. As we continue in game development, polymorphism allows for dynamic behavior. For example, different objects like player and enemy may use the same method such as attack, but the implementation will vary based on the object type. Encapsulation also plays a vital role as each object manages its own state such as health or score, ensuring that the game logic is clean and well organized. Object-oriented programming is also widely used in GUI frameworks. GUI components like buttons, windows, and text fields are modeled as objects. These objects encapsulate their own properties such as position and size, and methods for handling user interactions like clicks or typing. Inheritance allows us to create specialized components such as submit button inheriting from a general button class. This makes it easy to reuse and extend components in the user interface. Building on the previous point, OOP allows for an event-driven approach in GUI frameworks. Components like buttons can handle events like clicks through methods that are defined in their respective classes. This modular approach allows for easy customization and extension. For example, we could have a button class with a clicked method which could be overridden in different subclasses for different buttons action. Object-oriented programming is also heavily utilized in web development. For example, in an online shopping system, we might have classes for user, admin, and guest, each with different permissions. Inheritance allows for the creation of specified user types, while polymorphism ensures that actions like login behave differently for each user role. OOP structures web applications in a modular and flexible way, ensuring scalability and ease of maintenance. Continuing with web development, OOP is crucial for creating systems like a shopping cart. In this system, classes like cart, product, and order are used to manage the shopping process. Operations like adding or removing products are encapsulated within the cart object. Inheritance allows different user roles, such as members or guests, to interact with the cart in unique ways, enabling personalized user experiences. As we wrap up, let's review the advantages of using OOP in large systems. One key benefit is modularity. Large systems are broken down into smaller, more manageable components. Reusability is another advantage as classes and objects can be reused through the system. OOP also promotes maintainability by separating concerns and keeping code clean and organized. Finally, OOP ensures scalability, making it easier to extend systems as they grow. To recap, object-oriented programming helps in structuring large systems in a way that is easy to manage and scale. It promotes code reusability, maintainability, and flexibility. By using inheritance, polymorphism, and encapsulation, developers can design complex systems that are easier to understand, extend, and maintain. Now, let's put the concepts into practice. Your task is to design a library management system. The system should include classes like book, user, staff, and library. Implement methods for borrowing and returning books as well as searching for books. Use inheritance and polymorphism to model different user roles and interactions. Share your design with your peers for feedback. Thank you for your attention. To conclude, object-oriented programming is a fundamental paradigm that is widely used in real-world systems. By constructing code around real-world objects, OOP makes it easier to manage complex applications. For further learning, refer to object-oriented design and programming books and documentation. I encourage you to apply these principles to your own projects. Welcome to day 25 of our object-oriented programming course. In today's session, we will be planning and starting to build a mini project, a hotel booking system. This system will cover key concepts of the object-oriented programming such as classes, objects, and methods to create a functional application. Our objective today is to lay the foundation for our hotel booking system. We will be focusing on three key components: rooms, bookings, and customers. We will start by defining the basic structure and relationships between these components, and later we will add advanced features in the next sessions. Before diving into coding, it's important to define the scope of our project. We aim to create a simple hotel booking system that allows users to book rooms, check availability, and store customer details. Our key components are the room, customer, and booking classes. Each will have specific attributes and methods to manage the booking process. Let's now look at the design of our classes. We will need three main classes: room, customer, and booking. The room class will handle details like the room number, type, and availability. The customer class will store customer information, including contact details and booking history. Lastly, the booking class will link customers to rooms and manage the booking process. Let's take a closer look at the room class. It has a few key attributes: room number, room type, price, and availability status. The methods within the room class will include checking availability, booking a room, and releasing a room once the booking is complete. These methods will help manage the core functionality of our hotel system. Moving on to the customer class, this class will store information about the customer, such as their name, contact details, and booking history. We will include methods like viewing the booking history and making new bookings. The customer class will interact with the booking class to create and manage bookings for the rooms. Next, we have the booking class, which links the room and customer classes together. It will store booking details such as the customer making the booking, the room being booked, the booking date, and the duration of the stay. Methods within the booking class will allow us to create, cancel, and display booking details. However, here's an example of how the room class might look in code. We define the room number, room type, price, and availability status as attributes. The methods check availability, book room, and release room will be used to manage the room's booking status. This simple implementation ensures that we can easily manage room availability and bookings. Now, now that we have set up the basic structure, it's important to think about the next steps. We will be focusing on class interactions, where the customer class will create instances of the booking class and the booking class will manage the relationship between customers and rooms. We will also begin testing the basic functionality such as creating rooms, checking availability, and making bookings. Here's a simple example of how we can test our code. In the main function, we create instances of the room class, check if the rooms are available, book them, and then release them. This testing ensures that our room class methods are working as expected. Before we wrap up, here are a few tips for success. First, start simple. Focus on building the core functionality before adding extra features. Use object-oriented programming principles to keep your code modular and maintainable. Document your code with comments to make it easier to understand and remember to test regularly to catch errors easily. Finally, build iteratively, adding features as you go. To conclude, by the end of today's session, you should have the basic code for the room, customer, and booking classes. You should also have conducted initial tests to ensure the core functionalities such as room creation, availability checks, and bookings are working as expected. In the next session, we will focus on adding advanced features like polymorphism and file handling. Welcome to this presentation on the hotel booking system part 2. In this session, we will explore the advanced features of the system including polymorphism, file handling, and error handling. Let's dive into the technical aspects of building a robust and scalable hotel booking system. Let's begin with a quick recap of part 1. We developed the core structure of the system with three main classes: room book, booking, and customers. We implemented basic features such as booking rooms, displaying available rooms, and managing customer data. In part 2, we will add we will add more advanced features to enhance functionality and efficiency. Now let's dive into polymorphism. Polymorphism is a core concept in object-oriented programming. It allows us to use methods in a flexible and dynamic way depending on the object type. For our hotel system, polymorphism will help us handle different types of rooms like standard, suite, and deluxe, each with its unique pricing and features. This approach ensures that the system is scalable and can be extended easily. To implement polymorphism, we first create a base class room that contains a method calculate price which will be overridden by each derived room type. This ensures that each room class can have its custom price calculation method. Let's look at the code snippet for the base class. In this slide, we have derived classes for different room types. Each class inherits from the base room class and overrides the calculate price method to provide its own pricing logic. This allows us to calculate the price dynamically based on the type of room selected by the customer. Next, we move on to file handling. File handling is essential for storing and retrieving data between program sessions. In our hotel booking system, we need to persist customer and booking information. By saving data to a file, we ensure that it is available even after the program exists. We will explore how to write and read data from a file using file streams. Here's how we save booking information to a file. We use the offstream class to open a file in append mode. When a new booking is made, we save the room number and the customer's name to a text file. This ensures that booking data is preserved even after the program ends. To load the bookings when the program starts, we use the ifstream class to read data from the file. The load bookings function retrieves the stored booking information and loads it into the program. This ensures that when users check the availability of rooms, the data is up to date. Error handling is an essential aspect of building reliable software. In C++, we use exceptions to catch and handle errors. In our hotel booking system, we need to handle invalid inputs, file read-write errors, and other exceptions like double booking. This helps ensure that the system remains stable even when things go wrong. Let's look at how we can implement error handling. We create a custom exception class, booking exception, to handle errors like double bookings. This exception will be thrown whenever an attempt is made to book a room that is already reserved. It ensures that the system handles the error gracefully without crashing. Here we see how to use the custom exception in the book room function. If the room is already booked, the function throws a booking exception. This prevents users from making invalid bookings and ensures the integrity of the system. To enhance user experience, we implement a menu-driven interface. This interface allows users to easily navigate through different options such as booking a room, viewing available rooms, or checking existing bookings. It's simple and intuitive, ensuring that users can interact with the system effortlessly. To handle user input, we use a loop and switch statement. This allows the program to continually display the menu and take input until the user chooses to exit the system. It also ensures that the user can make choices easily and get the appropriate response from the system. After implementing all features, it's time to test the system. We need to ensure that room bookings work correctly, file saving and loading functions as expected, and errors are handled properly. Additionally, we should document the entire system, including class and method descriptions, to ensure the project is maintainable and understandable. As we consider advanced improvements, we can explore more sophisticated topics. For example, we can expand the class hierarchy to include more specialized room types. We can also use more complex file formats such as JSON or XML for better that data storage. Additionally, we could develop a graphical user interface to provide a richer experience for users. To summarize, in this session, we have enhanced the hotel booking system by adding advanced features like polymorphism, file handling, and error handling. These additions improve the flexibility, reliability, and scalability of the system. Moving forward, you can build on this foundation to add more features and further improve the user experience. Welcome to day 27, Debugging and Optimization in Object-Oriented Programming. In this session, we will explore key techniques and best practices for debugging OOP code and optimizing its performance. Let's begin with debugging. Debugging is the process of identifying and fixing errors, commonly known as bugs, in your code. It ensures that the program behaves as expected and helps improve code quality and reliability. It's an essential skill for every programmer. In object-oriented programming, we encounter several types of bugs. These include null pointer exceptions, where we try to dereference a null reference, and incorrect use of inheritance or polymorphism. We also deal with memory leaks, where memory is allocated but not deallocated, and logic errors, where the algorithm does not work as intended. It's important to recognize these common bugs to fix them efficiently. Let's look at some common debugging techniques. First, we have print statements. This simple technique allows you to display variable values at different points in the program, helping you understand the flow of control. Another common technique is using breakpoints. By setting breakpoints in your IDE, you can pause execution and inspect the state of your program step by step. Next step through debugging allows you to go through your code line by line. This helps in tracking down errors in more complex sections. Additionally, unit testing is crucial. Writing unit tests for each part of your code ensures that components behave as expected and makes it easier to isolate and fix bugs. Memory management refers to how memory is allocated and deallocated during the execution of a program. Improper memory management can lead to crashes and memory leaks. In languages like Java and C Sharp, garbage collection handles memory management automatically. However, in languages like C++, programmers are responsible for manual memory management, which requires special attention. In C++, memory management is done manually. You use the new keyword to allocate memory and delete to free it. However, improper memory management can cause issues like memory leaks or dangling pointers, which occur when memory is freed and then accessed again. It's essential to handle memory allocation and deallocation carefully to avoid these problems. To help with memory management, C++ provides smart pointers. These include unique pointers, shared pointers, and weak pointers. Unique pointers take ownership of objects, shared pointers allow shared ownership, and weak pointers prevent circular references. Using smart pointers automatically handles memory deallocation, helping to prevent memory leaks. Optimization is about improving the performance and efficiency of your code. It's critical for handling large-scale applications and ensuring that your program runs smoothly. Optimizing your code involves reducing memory usage, improving processing speed, and maintaining clean, readable code. Let's explore some techniques for achieving this. One optimization technique is avoiding redundant object creation. Instead of creating new objects repeatedly, reuse them wherever possible. Another method is reducing method overhead. Frequent function calls can slow down your program, so consider inlining small functions to minimize this overhead. Next, caching and memoization are powerful optimization techniques. By storing the results of expensive computations, you can reuse them later without recalculating. Also, using efficient algorithms is key to optimizing your code. Choosing the right data structures and optimizing algorithm complexity can drastically improve performance. Now, let's look at an example. The first step in debugging is to understand the code thoroughly. Review the provided code carefully and identify where the bugs might be based on the symptoms you observe. Once you have located the problem, use debugging techniques like print statements or breakpoints to identify the exact issue. Once you have identified the bugs, the next step is optimization. After fixing the bugs, review the code to see if there are any redundant operations or inefficient data structures. Look for areas where you can improve performance or memory usage. Here are some best practices. Code reviews are one of the most effective ways to identify bugs early and suggest optimizations. Refactoring is another important practice. Regularly revising your code to improve its structure and efficiency. Finally, profiling tools like gproof or visual vm can help identify bottlenecks and optimize your code further. To conclude, debugging and optimization are key to writing efficient, reliable OOP code. Debugging helps identify and fix bugs, while optimization ensures that your code runs faster and uses resources more efficiently. As you work on real-world projects, practicing these techniques will help you become a more skilled programmer. Welcome to day 28 of your object-oriented programming journey. Today is all about revising and practicing advanced OOP topics. You will be diving deep into real-world coding challenges and enhancing your mini project by integrating advanced OOP principles. We will also take time to review and optimize your work, ensuring that you reflect on your learning process. Let's get started. Let's begin by revisiting some of the core advanced OOP principles. First, we have design patterns. These are reusable solutions to common design problems. Some examples include singleton, factory, observer, and strategy patterns. Understanding these patterns will help you solve complex software design issues effectively. Next, we have the solid principles. These are 5 key design principles that ensure your code is maintainable, scalable, and easy to understand. We will take a closer look at each principle. Single responsibility, open or closed, Liskov substitution, interface segregation, and dependency inversion. These principles are the foundation for writing robust and flexible object-oriented code. Continuing with our revision, let's talk about inheritance. This allows you to create a class based on another class, inheriting its properties and behaviors. But be careful, overuse of inheritance can introduce unnecessary complexity. Next is polymorphism, a concept that allows objects to behave differently depending on their type. We will discuss both compile-time polymorphism through method overloading and runtime polymorphism through method overriding. Finally, we have abstract classes and interfaces. Abstract classes allow you to provide a common base for your subclasses, while interfaces enforce a contract that classes must follow. Understanding when to use each of these is essential for designing clean, reusable code. One of the key concepts in building resilient software is exception handling. In OOP, we use exceptions to manage errors in a structured way. Consider exceptions. Custom exceptions allow you to handle specific errors more gracefully. It's crucial to follow best practices when working with exceptions. This means using try-catch blocks appropriately and avoiding using exceptions for control flow. Here's an example you might create. Here's an example. You might create a custom exception for handling negative age inputs in a user profile system. Now it's time to practice. Let's apply the concepts we have just revised to real-world coding problems. For example, implementing design patterns like singleton and factory in your projects will help you manage resources and create objects more efficiently. Polymorphism and inheritance can be used to solve problems with method overriding and overloading, such as modeling real-world objects like vehicles or animals. You will also get the chance to refactor your code using solid principles, which will improve the maintainability and scalability of your system. As you continue enhancing your mini project, start by incorporating advanced OOP features. Design patterns like the factory and singleton are perfect for structuring and managing different components in your project. Additionally, refactor your code to follow solid principles, breaking down large classes into smaller, more focused ones. Don't forget to implement exception handling to ensure your project can gracefully handle unexpected situations. Let's take it a step further. Add new features to your mini project such as user authentication, logging, and data validation. This will make your project more robust and production ready. If your project needs to handle large datasets, consider implementing caching for better performance. Optimizing your algorithms and reducing redundant code will also help ensure that your project scales well. Once you have added new functionality, it's time to review and optimize. A thorough code review is essential. Check for readability, maintainability, and efficiency. You will also want to focus on performance optimization, especially in areas with high time complexity. Consider adding caching or lazy loading where appropriate. Be sure to seek feedback from your peers or mentors as they as their input can help you make your project even better. Take a moment to reflect on your learning journey so far. Think about the challenges you have faced while grasping advanced OOP concepts such as design patterns or solid principles. How did you overcome those challenges? Celebrate your key achievements like successfully applying these concepts in your mini project. Finally, think about your next steps. What areas do you still need to improve, and how can you continue to grow as a developer? Looking ahead, day 29 will be all about testing your knowledge. You will be taking a comprehensive quiz covering everything you have learned so far. This will help you gauge your understanding of advanced OOP concepts. You will also have the opportunity to practice coding problems and mock interview questions. This will prepare you for the challenges ahead and help you feel confident in your OOP skills. Welcome to day 29, final quiz and mock interviews. Today we will be focusing on reviewing and reinforcing all the object-oriented programming concepts we have learned. We will dive into a comprehensive quiz, work through coding problems, and simulate mock interview scenarios. Let's get started. By the end of today, you will have the opportunity to test your knowledge through a comprehensive quiz that covers OOP fundamentals, advanced topics, and real world applications. You will also practice solving coding problems and experience mock interview conditions. This will help solidify your understanding of OOP principles and get you ready for interviews. The quiz today will assess your grasp of object-oriented programming, starting with foundational concepts and moving to advanced topics. You will also be tested on your ability to apply these principles to real-world scenarios. Let's take a closer look at what you will be tested on. In the first part of the quiz, you will face questions that test your understanding of core OOP principles, classes, objects, inheritance, polymorphism, encapsulation, and abstraction. This section will check how well you can implement basic OOP concepts in code. The next set of questions will challenge you with more advanced OOP concepts, including design patterns like singleton and factory, as well as solid principles. You, you will also need to demonstrate your understanding of memory management and how to handle exceptions in your code. In the final section, you will tackle real-world application problems where you will design class hierarchies, identify relationships like has-a and is-a, and model systems like hotel booking or inventory management systems. This part will test your ability to apply OOP in practical scenarios. After completing the quiz, you will work on coding problems that range from basic to advanced. These problems will help you practice implementing OOP principles in different situations. Let's explore the different levels of coding challenges you will encounter. First, you will begin with basic OOP problems. These problems will test your ability to design classes with attributes and methods, implement inheritance, and demonstrate polymorphism. The goal here is to solidify your grasp of the building blocks of OOP. Next, we will move to intermediate level problems. Here you will apply design patterns like singleton and factory and work with abstract classes and interfaces. These problems will help you practice using OOP principles in more complex scenarios. Finally, you will tackle advanced OOP problems. These challenges will focus on dynamic memory management, exception handling, and more complex uses of OOP concepts like dynamic polymorphism and deep cloning of objects. You will need to demonstrate your ability to optimize code while ensuring its correctness. Mock interviews are a great way to simulate the pressure of a real technical interview. In this part of the day, you will practice solving coding problems and answering OOP design questions in a timed environment. This experience will help you become more confident in explaining your thought process. During your mock interview, you may be asked to design systems like a bank account or file management system. You will need to demonstrate how to implement OOP principles like inheritance and polymorphism. Expect to explain your approach and discuss trade-offs in your design choices. In addition to technical questions, mock interviews often include behavioral questions. These questions assesses your problem-solving approach, communication skills, and your ability to handle challenges in a collaborative environment. Practice articulating your thought process clearly and confidently. Mock interviews often have strict time limits, so managing your time efficiently is crucial. Focus on writing clean, efficient code while explaining your approach. If you are unsure, it's always better to ask clarifying questions than to make assumptions. Here are some tips for success. Stay calm and focused throughout the quiz and mock interviews. Think out loud to demonstrate your problem solving process. Practice regularly to improve your coding speed and clarity. And most importantly, enjoy the learning process. By the end of day 29, you will have completed a comprehensive quiz, solved coding problems, and participated in mock interviews. This will leave you well prepared for technical interviews. Remember, OOP is all about practice and clear communication. Keep honing your skills and you will be ready to succeed. Welcome to day 30 of your object-oriented programming course. Today we will focus on showcasing your learning journey. By the end of this session, you will have the opportunity to present your mini project, reflect on what you have learned, and create a portfolio entry that highlights your skills in OOP. Let's dive into these exciting activities. Let's start with the first step, presenting your mini project. The goal here is to demonstrate what you have learned through this project. When presenting, make sure to highlight the problem your project solves, the design and architecture, and how object-oriented programming principles were applied. Showcase the core functionality and the features that make your project unique. When presenting your project, focus on the following key aspects. First, explain the problem your project solves. What real-world issues does your system address? Next, describe the design and architecture of the system. Discuss the classes, attributes, and methods you used. Then emphasize the advanced features such as polymorphism, file handling, or exception handling that you have integrated. Don't forget to talk about the challenges you faced and how you solved them. Finally, consider discussing any future enhancements you envision for the project. Now let's move on to the reflection part of your journey. Reflecting on your learning process will help consolidate your knowledge and allow you to see how far you have come. In your reflection, you should cover your initial expectations, the key things you have learned, the challenges you encountered, and what growth you experienced. This is an important part of your learning process. Start your reflection by discussing your initial expectations. What were your goals at the start of the course? What skills or concepts did you hope to learn? Understanding your starting point will help you measure your growth and give you a clear view of your progress. Next, focus on the key learnings from the course. What were the most valuable concepts you picked up? Perhaps it was understanding the core principles of OOP, like inheritance, polymorphism, and encapsulation. Or maybe you gained new coding techniques. Reflect on how these learnings have impacted your skills and shaped your understanding of object-oriented programming. Every journey has its challenges, and OOP is no different. Think about the most difficult problems you faced during the course, whether it was understanding a complex concept or debugging a tricky issue. These challenges have contributed to your growth as a developer. Reflect on how you overcame these obstacles and how they helped you improve your skills. In this section of your reflection, talk about the skills you have gained. You have not only learned how to program in a object-oriented style, but also how to think critically and solve complex problems. Finally, share your future goals. What would you like to learn next in the realm of software development? Maybe you are interested in learning design patterns or contributing to open source projects. Now let's shift gears and focus on creating a portfolio entry. A well-crafted portfolio entry is a powerful way to showcase your skills to potential employers or clients. Your portfolio should highlight your project's features, the technologies you used, and how you applied OOP principles in your work. A strong portfolio will demonstrate your problem-solving abilities and your technical knowledge. Start your portfolio by summarizing the project. Provide a clear and concise description of the project's purpose. What problem does it solve? Be sure to also mention the main features or functionalities you implemented. This will give potential employers a good understanding of what your project is about. Next, list the technologies you used in your project. Be sure to mention the programming languages, tools, or frameworks you leveraged. This helps to show the technical breadth of your skills. It's also a great way to highlight your experience with industry standard tools and technologies. One of the most important aspects of your portfolio is demonstrating the OOP principles you applied. For example, explain how you used inheritance to create a hierarchy of classes or how polymorphism allowed for flexible methods calls. Make sure to showcase how you used abstraction and encapsulation to make your code more modular and maintainable. To further demonstrate your skills, include relevant code snippets in your portfolio. Choose examples of code that showcase your understanding of OOP concepts such as class definitions, method implementations, and object interactions. Briefly explain each snippet so that potential employers can understand the logic behind it. Every developer faces challenges during a project. In this section, talk about any hurdles you encountered while working on your project. Whether it was a tricky bug or a design decision, discuss how you tackled these challenges and found solutions. This shows problem-solving skills and resilience. A picture of a picture is worth a thousand words, so don't forget to include screenshots or a live demo of your project. If your project has a user interface, include clear and professional screenshots. If possible, provide a link to a live demo or a video walkthrough to give potential employers a hands-on experience with your project. To make your portfolio stand out, add a personal touch. Be clear and concise in your descriptions, but also give some insight into your thought process. Explain the design decisions you made and the reasoning behind them. Update your portfolio regularly with new projects and improvements, and ensure that it looks professional and is easy to navigate. Preparing for real-world applications is crucial as you transition from learning to applying your skills in professional environments. Keep building projects to refine your abilities. Contribute to open source projects to gain feedback and collaborate with others. Prepare for interviews by practicing explaining your projects and the OOP concepts you applied. Congratulations on completing the course. You have built a mini project that demonstrates your proficiency in object-oriented programming. But remember, this is just the beginning. Keep practicing, continue learning, and apply your skills in real-world projects. Your OOP journey has only just started, and the future is full of exciting opportunities.